Okay, before we start, a couple of reminders. Just unmuted the mic. So the mics in this room are very sensitive, so if there's something you don't want recorded, please wait till after the talk. Secondly, there's another theory talk today, so we have a double feature. At 12:30, Liren will be giving the talk. And now it's an honor to introduce Irit Dinur from the Institute for Advanced Study in Princeton. Irit has worked on many different aspects of theoretical computer science, more towards complexity theory. She's a leader in the area of PCPs and probabilistically checkable proofs. Also, she's one of the co-founders of Differential Privacy and has been taking very different approaches or new approaches to it through locally testable codes and then through high-dimensional expansion. Recently, her work has been recognized by many awards, including the Gödel Prize, the Paris Kanellakis Theory and Practice Award, the Erdős Prize, multiple Best Paper Awards. And Irit is also like a personal role model for me. It's tried doing whatever the things Irit is working on. And it's great to welcome her at TTIC.
Thank you so much, Madhu. It's really a pleasure to be here, and thanks for the too generous introduction. And please, I tried to make the talk accessible, and don't hesitate to slow me down and ask me questions if you can. Okay, so the name of the talk is Local to Global in High-Dimensional Expanders, but let me already start and tell you I'm really going to talk about expanders and how they relate to other questions in theoretical computer science. Okay, so an expander, hopefully we all know what it is. It's just a graph that's very highly connected despite every specific node only having few edges. And this has been tremendously useful in computer science and also in mathematics more generally. So we have many applications. Some of them are very natural, like the fact that the graph is very well connected means it's useful for kinds of robust networks. And it's good for random walks converging quickly. But some applications are more surprising, like why would it be useful for de-randomization? Maybe you can have a sense, but because it behaves like a very dense graph, even though it's very sparse, so that's some de-randomization aspect. Going further down the list, why would an expander be useful for error correcting codes? I think that's less obvious. Maybe some of you, if you work with Maduro, you've heard about these things and it's not surprising to you. But I think a priori it's very weird why it would be useful, and similarly for PCPs. So these are the kinds of things I want to talk about. And so my plan, I want to cover three things. All of them have a kind of local to global aspect, which I clarify maybe what I mean. I think local to global is a buzzword that a lot of people use for a lot of different reasons, so I'll say what I mean. So the first one, I want to talk about expander codes and just say what they are in a way that maybe sets the stage to the later items. So I don't know how many of you know expander codes, but I'm not going to assume. So tell me if I'm going too quickly or something, just let me know. Then I'll talk about a specific part in how to prove the PCP theorem that also has this very strong local to global feature. And then I'm going to move to something more recent, which is these locally testable codes. And in all of these, we'll see expansion and local to global. I'm going to start with expander codes. So for me, for this talk, an error correcting code is just a linear subspace of 0, 1 to the n. So it's a collection of strings. And you want that every two strings are far apart. The use of this, there are so many uses of this, but in particular, when two strings are far apart, you know that if a few bits got flipped, there's only a unique original string that you can. That's an error correcting code. And we know already from a long time ago that random sets of strings are very good. Even a random linear space is very good. This was proven by us. Also, if you choose a random sparse matrix, so every row will only have a constant number of non-zeros, The kernel of this matrix will be a very good code with high probability. So all these are well known. And Sitter and Spielman in the 90s showed that if you use an expander, you can also define a code that is a very good correcting code. And in their construction, there is some local to global aspect which I want to talk about. So let's see what they do. So start with an expander graph that's we think of the bipartite graph, and the picture is not so good because we think of like the bits on the left and the parity checks on the right, so it needs to be slightly unbalanced. It should be less vertices on the right and on the right and on the left. And then you look at this graph and you just write down its adjacency matrix, and you view it as a parity check matrix. So what this means is that any vector that kind of satisfies all of it sums to 0 on every red point. So you put the bits here. That's what it means to be in the kernel, and then you put the bits to this side, and every vertex here on the right sums the bits and needs to come up with 0. If that happens, it means your word is in the kernel of the matrix or it's in the code. So, okay, why would being an expander have anything in relation to being a code, to having good distance? So what I need to ask myself is, if I have two different strings in this code, how far apart are they? So since everything is linear here, if I have two strings that are different, I can take their difference, and I have a non-zero string in my subspace. And I need to ask myself, how many ones can this string have? What is the weight? The more ones that I can convince myself that I have, it means that this code has large distance. Those original two strings were far apart. So this really, you can describe it as a kind of expansion. So here the code is the kernel of the adjacency matrix. And the kind of expansion that I need is unique neighbor. It's a kind of expansion that if you look at a set of vertices where your string is non-zero, then you look how many neighbors are on the right, you see only a unique neighbor in this set. So if you have a neighbor on the right that sees one element in the set of ones and all the other neighbors are in 0, it means that the sum is not 0. So it means that this set of ones cannot be a code word. Okay? Yes?
So you said it requires unique neighbor expansion, but it would be good enough if it was like an odd number of neighbors?
Yeah, thanks. That's true. So really, the necessary and sufficient is odd neighbor expansion, but we don't have a handle on that. We don't know how to do that, so we say unique neighbor. But unique neighbor and odd neighbor, both of them, we actually don't have a very good handle. We don't know how to construct these things so easily. So that's not quite correct, but at the time of the Sipser and Spielman paper, we didn't know how to construct unique neighbor expanders. So they weren't satisfied with this construction. They did something else. What we know how to construct much easier is spectral expanders. So talk about that a bit. But it's a weaker, more analytic requirement for a graph to be an expander. It's something that we have a lot of construction. So I'm going to move to their second construction of expander codes. And here, there's two components. One component is a graph, an expander graph. And you see in the picture, it's like, you should think of every vertex it's deregular, so every vertex has some d neighbors. It's not bipartite anymore. And there's many, many vertices. It's a big graph. But the point is that the graph is a very good expander. So what does that mean? Here, the requirement is that the second largest eigenvalue is bounded away from so the top eigenvalue in a deregular graph is t, and the second largest eigenvalue is bounded away from d. It's called lambda. Okay. So this has to do with the connectivity of the graph and kind of equivalent to having the edge expansion. No matter how you cut the graph into two parts, a lot of edges will cross. One component is this expander graph. The second component is a small constant code of length d. So here I wrote down some examples. So it's just a collection of strings of length. So these are constant length strings, length d, and you want that the minimum distance of this code is some delta 0. And the requirement will be that delta 0 is larger than lambda, some kind of trade-off. And what will be the code? So we already have it written here. The code will be all the strings where you put a 0 or a 1 on an edge, on every edge of the graph, and you have that restriction of your code to EP. This is like a set of neighbors of a vertex. So basically, I look around the vertex and I look at all the bits, and I see that I can collect them into a little string, and then I need to check that this string belongs to my base code. It's a definition. I think now I will move. So I didn't figure out how to do it with the iPad, so I'm sorry. I have to move between things. Okay. So I want to kind of focus a bit more slowly on this. Nothing difficult, it's just it will help me continue the talk later. So I have here part of the graph, and I'm thinking there is some string which labels all the vertices, all the edges, sorry, by zeros and ones, right? So I have these bits everywhere. And I want to know if it's in the code or not. So basically what I do is for every vertex, I collect the bits from the edges touching this vertex, and I collect them into a little substring whose length is exactly how many edges touch this vertex, and I need to make sure that this is in the code. Okay, that's how we define the code. So for every vertex, I have a little string. And an alternative way to view this is that don't give me the bits on the edges. Instead, you give me the little code words for every vertex. So alternatively, you could have told me, look, I'm giving you a code word here on this vertex that belongs to the little code. I'm giving you a code word here that belongs to the little code, and so on everywhere. And what I'm promising you is that along every pair of edges, these code words agree with each other. So maybe I have another picture that I drew. Yeah. So in this picture, you see that really like the neighbors of a vertex, they also need to be labeled by which coordinate of the string you are. And then really this code word needs to agree with the code word of some neighbor on the appropriate coordinate. So if this is a pink coordinate and that is a pink coordinate, they just need to agree. So it's like a bunch of local code words that are stitched together in some way that the graph tells me, and they all need to agree with each other. And if you manage to do this assignment of local views that all agree together, you got a code word. And if it's not a code word, then at some point there will be some mismatch. Yeah.
So in this picture, it has this like consistent labeling property where if you're my third neighbor, then I'm your third neighbor. Is that like important? Are you gonna require that, or is it okay if
I'm not requiring that. And notice that I actually don't have it. You're my first neighbor, but that guy, you're my last.
I see. The pink doesn't mean first.
I'm not requiring that.
Thank you.
But it's a good point, and it's not important, but it is important that I specify like which neighbor you are. Otherwise, the code won't be defined. But that doesn't matter. Okay. So what? So I want to say that this code is like saying, on a lot of local views, you belong to some small code, a local code, C0. And you kind of stitch them together using this expander. And I want to say that this gives me some good properties. So property that is first and most important to check is that this new stitching together code has large distance. Okay, so why would it have large distance? So maybe before I say the large distance, just to say, so you can really think of like two equivalent ways to define the code. The first is to say you label a 0, 1 label for every edge, So your code word is like a string of length E. And the requirement is that, around every vertex, the collection of bits needs to be in the smart code. And alternatively, you give me a little code word for every V. So like in changing the way I'm viewing the bits, you're giving me a code word for every vertex, and now I'm requiring that along edges, the two local views need to match. It's equivalent. Okay, so now why would I like this construction, or why is it good? Why does it have good distance? Well, the thing is, here is where we use the expansion. So here is where we use the expansion, because suppose you had a non-zero code in this construction. So you had some labeling of all the edges. It's not zero somewhere. So on some edge, you're not zero. Then what would happen is that around that vertex, so imagine that on this edge the string is not zero. Then it means that around this vertex, what you see is a code word of C0. And C0 locally, we know it has distance, so there's a few non-zeros. So it means that not only this edge has a 1, but several other edges also have a 1. Okay, so I already kind of have some local behavior that if I have a single non-zero, it means that I have a few more. But then I can go to these neighbors, and each one of them has now a single non-zero, and so they have a few more. And, this propagates. And if you're in an expander, part of properties of an expander is that this propagates everywhere, and you've proven that any word that is non-zero must have many, many non-zeros. And in fact, kind of to prove it formally is very simple once you have the idea. So the conclusion of this is that we have a local to global property where the local distance of C0 kind of propagated to the distance of the global code. So this is very nice local to global, but one thing that it doesn't have is robustness. So what happens if you give me a string and you know that it satisfies these conditions everywhere, except for maybe one place. So in your string, on every vertex, when you look around the edges, it belongs to the local code. But there's maybe one vertex where this doesn't happen. Your string doesn't belong to the local code. So, it satisfies almost all the local conditions, but maybe a few of them are violated. Even at the extreme, one of them is violated. What can you expect to know? Usually, like in a property testing setting, we like to have this kind of robustness feature that, okay, there's a bunch of local constraints, and even if you satisfy 99% of them, okay, maybe you're not exactly in the code, but you're close to being in the code. This is the kind of thing we would like. But unfortunately, this is not true. And this is a work by Ben Sasson, Harsha, and Rashkodnikova. I'm almost sure they were postdocs here at that time at TTI. At least Ben Sasson and Harsha.
2 out of 3.
What?
Yeah, 2 out of 3.
2 out of 3, yeah. So they looked at these expander codes and they realized that it's not the case. You can come up with strings that violates only very few constraints or even one and still be in the code. So this code has, there is some aspects of local here where the constraints are very local, but there isn't a robustness. Like you can't deduce global properties from satisfying almost all the local constraints. So that's not like a property testing kind of behavior. And why would I even imagine such a thing exists? Well, in other kinds of codes, we do have this behavior, like in the low-degree polynomial codes. So if I look at these two pictures, I have here the line versus line low-degree test. So you can think of this is a Green-Muller code. It's a code where all the code words are low-degree functions over some finite field vector space. And this code also has a local view characterization. You can say along every one-dimensional line, the function looks like a univariate low-degree polynomial. So there are these local tests. But here somehow, if you say, give me a function that on a finite field vector space such that it's low degree on almost all the lines except for on one line where I don't care. It turns out that it's the same set of functions. You know, if you already low degree on every other line except for this one, you're forced to be low degree also on this one, so it won't change anything. So another way of describing this code is to say, for every line, give me a small code word, which is a code word in a Reed-Solomon code, so basically a univariate code word. Give me like a table of local views. For every line, you give me the evaluation on this local view, and then I need to check that two local views agree with each other. So this is trying to describe a situation that is analogous to the situation here, where for every vertex you gave me a little local view, and these local views somehow need to match with each other. So but somehow here in the case of low-degree polynomials, there is more redundancy than just the fact that these local views intersect. And in fact, if you remove the requirement that you're low degree on one of these, the dimension of the code doesn't increase. Whereas if you do it in the expander code, so how did Ben Sasson, Harsha, and Rishkov prove the result? What they said is that, look, if you look at this entire graph and you look at the local codes everywhere, imagine that on one of the local codes you remove one of the linear constraints. Then the space of all functions that live in this space, maybe the dimension grew by 1. If the dimension grew by 1, you've got now a new code word that was not there before, but now it actually it satisfies all of the local constraints except here where it's new, so it didn't satisfy the constraint before, and now it does. So this code word will be very far from your code, but only violate one constraint. So this kind of behavior cannot exist in the case of low-degree polynomials, because when you remove the constraints of one line, the space of function just doesn't grow. You stay in the same space of function. Okay, and here I have another example where you do the plane versus plane. Maybe I will talk about another kind of code, which is tensor codes. So here are tensor codes that are defined by two base codes, say two copies of the same base code C. And the code words in the tensor code are all tables, like n by n tables, the matrices, where the rows are, each row belongs to C and each column belongs to C. So that's my code. And also this code you can view as like a collection of local views, where each column is a local view and each row is a local view. And kind of an alternative way to view it is that you give me the code word for every line, for every row, you give me the code word for every column, and you promise me that these code words agree with each other. Okay? So that would be the equivalent way to think about it. And now the question is, if you want to understand if this is a robust kind of definition or not, you can ask, well, what if I tell you that I got this collection of rows and collection of columns, and most of them agree with each other? I'm not telling you that all of them agree, just most of them agree. Does this mean that you can kind of fix them a little bit and get a collection there that everyone agrees with? Okay, is the question clear? So I get a collection of rows, a collection of columns, and I know that most of them agree with each other. This question was actually initially thought about in the case of low-degree polynomials. So you think of a bivariate polynomial, so a polynomial in x and y. And then when you fix x to be some number, you get a specific column, like a polynomial in y. And when you fix y to be some element in the field, you get a specific row. And so you're told, look, you have this function in x and y. for most of the x's, the function has low degree in y. For most of the y's, the function has low degree in x. Does it mean that this function is close to being low degree? Okay, and this is a more general way to ask it for a general tensor. Okay, so this was studied first by Ben-Sasson in Sudan for tensors, and they weren't able to analyze the two-dimensional case. They didn't know what the answer is, but they managed to analyze a 3D tensor, so C tensor, C tensor, C. And they showed that such a robust statement holds. So it was kind of remained open question whether the 2D case is true or not. And then Paul Valiant actually found an example of a code C such that this doesn't hold. So you have a code C where the tensor, even if you can find rows and columns that are almost agreeing, there is no way to fix it to a perfect tensor code. So that was very kind of intriguing. And we managed to find Sudan and Avi Wigderson kind of more properties for the base code C to force this to happen, to force this kind of robustness, so that if the local views agree, you can fix it. And there was some improvement of this by Ben-Sasson and Biederman. So for tensor codes, we have this situation where for some codes, you have this property, for some base codes, and for some base codes, you don't have this property. Robustness. So if you satisfy almost all constraints, it's already has some global implication that you're close to some global code. Okay, I think now we're going back here. Okay, so just to kind of summarize the expander codes part, we saw a definition of an expander code, and we saw how you can define it by these local views and how the local distance kind of propagates to global distance. And we also saw that there is this local to global, but it's not robust. If you satisfy almost all the constraints, it doesn't mean anything about it. Yeah.
So can you compare this like robustness notion that you're talking about to like just like the general abstract notion of like a locally testable code? Like, is this
and thanks for the question. I'm gonna get there. I'm kind of leading towards the abstract notion of locally testable code, which just to say it's exactly this kind of thing where you have a bunch of parity checks, and even if you satisfy 99% of them, you must be close to it. And this is I feel that it's not just like a definition of a locally testable code, it's a general thing, like also in a PCP. You want to verify some NP statement, and you want to have 99% of the verification already have strong implications. Okay. So I just wanted to mention that there is a recent work by Madhur and his gang, Shashank Srivastava and Geronimo and Mikal. Yes. Okay, so where they show other kind of very surprising properties of the local code lift to the global code. In particular, like optimal list decoding behavior. If you have it locally, you will have it globally. Kind of this expansion allows you to get more mileage than I would initially expect. But maybe if you haven't heard about it, I recommend it. Okay, so. Okay, before I continue to PCPs and other areas, leaving codes a little bit, I want to tell you about expanders because we're using them very heavily, and do they even exist? So you know that random deregular graphs are very good expanders, just using a union-bound argument. We also know explicit construction, so a famous construction due to Lubotsky, Phillips, and Zarnak, and also to Margulis, uses some kind of heavy weight group theory, number theory. Basically, they look at the infinite deregular tree. That's the picture here. And then they view it as labeled by some group element so that you can quotient by a subgroup and basically glue the tree on itself and get a finite object that still behaves very much like the infinite deregular tree. And in particular, the spectrum, the eigenvalues are very well employed. So that's a very kind of efficient construction of an expander. And there is the famous zigzag product construction of Reingold, Vadan, and Wigderson, where they said, we want something more elementary. And they came up with a very elegant graph product that starts with two expanders and kind of keeps growing and keeps having them a constant degree. So interestingly, the second two items, both the LPS, the Ramanujan expanders from the infinite tree, and also the zigzag product, the way to analyze them is by using spectral methods. You really look at the eigenvalues. And that gives you some amount of mileage, but there are some properties that random graphs have that we don't know how to get in these areas. And in particular, the random graphs, you can also prove that they have this unique neighbor expansion, lossless expansion, and other properties that we are, with a lot of work, we can get some of these properties explicitly, but I would say less developed. So there are still a lot of open questions here. So now I'm going to talk a little bit about the probabilistically checkable proofs and what kind of use of expanders goes on there. So what is the PCP theorem? It's a very celebrated theorem from the beginning of the 90s. And it says that every NP statement can be encoded in a way that can be verified ultra fast. And one way that I like to view it is a gap amplifying encoding. So you start with some NP problem like graph recoloring. So you have a graph, you want to color the vertices so that no edge sees the same color as the endpoints. And the PCP theorem kind of transforms your graph to a new graph such that if the original graph had perfect coloring, so I wrote here val equals 1 the fraction of edges that see two different colors is 100%, then after this transformation, the new graph will also have this property. It will be perfectly three-colorable. But if your original graph was not perfectly three-colorable, so maybe you could color it so that almost all the edges are satisfied, but one edge is violated. Even in that case, after the transformation, you're guaranteed that some epsilon fraction of the edges will always be violated no matter how you try to color the graph. So it kind of amplifies the fraction of problems. Okay, so maybe you see that it's a bit similar to what I talked about in the codes, where you had a bunch of parity check constraints, and you were wondering what happens if I just violate one parity check? Can I be something completely different, or am I forced to be close to a code word? So here it's after this transformation, you see that if you started with a no case, with a graph that wasn't three-colorable, then after the transformation, it's not only that you violate one check, you violate the whole fraction of checks. Okay? So how do you kind of get this transformation, and how do you prove this theorem? So in the original theorem of yeah.
I'm a bit confused. So G, you're changing just the graph or also the coloring? Because this is first, you take a specific. This operates in a graph or in a color or a graph with a coloring?
Okay, relates also to our talk. So you change the graph, and when you change the graph, you change all the possible colorings.
Right. So how can you? But what good does it do me if I have this condition? I mean, can I easily check that a graph there's no coloring that satisfies that is good in epsilon?
No. So I mean, this is a polynomial time transformation, and this is an NP-hard problem. So it's not like, okay, I apply my transformation, and then here I can distinguish.
Okay.
No, it's still going to be NP-hard. But if you think of a situation where, suppose, I have a graph and I have a coloring, and I want to convince you that my graph is three-colorable, and you tell me, look, I don't have time to read your coloring.
Right.
Give it to me in a more efficient way. So we're going to, both of us, separately compute kind of this transformation from G to G prime. I'm going to also compute from the old coloring.
So, I see.
Compute a new coloring, and then you can check it. You can ask me, okay, so tell me what the color is of this and this and this edge. and you know that I have no way of cheating.
Right. So but you do need to be able to transform the coloring then also.
Yeah, so I didn't say it here, but like a stronger requirement would say that, okay, so firstly, we have a gap amplifying encoding from graph to graph, and you want to also be able to encode a witness to a witness. So if this value is 1 and you had a witness, like the coloring,
Yes. Okay.
you can compute it.
Now
with your
fine.
witness.
Okay.
Yeah,
Okay.
that's important.
Sorry.
In fact, so like, I don't know, I learned this thing when I was in grad school, and it's really fantastic. The reason it's fantastic is because it allows you, imagine epsilon is like 0.1. It means that if you read like 100 bits in the new graph, you've checked an NP-hard statement when you only read a constant number of bits. So kind of, it seems impossible. It's possible. But I remember people would often ask about this question, wait, but can you compute the new witness from the old witness? And I always thought, like, why are they asking this? It's not like you ever are going to use these things in real life. Why do you care about this? And of course, it's completely off because today these things are actually used in real life. They're implemented in blockchains where you want to prove to someone that you actually did the right transactions, and you're not going to send them the whole history of blockchain and the whole computation, but you really need a proof that's, adversarial resilient. Like, it's not like a proof that, you should believe me that I did the right thing. A lot of money is depending here on this being correct. So PCPs are used in blockchains, and maybe they'll be used in other applications. I think Nati has something in mind, so I don't know.
Okay, sorry. Is it important though that I can transform G in a way that's independent of the coloring? Like if I could do this transformation for a specific coloring, it seems that would be good enough in terms of the Probabilistically Checkable Proof. Is it like fundamental that its transformation is independent of the coloring?
It is fundamental because, if G actually has a value less than 1, I still need to be able to do this transformation. So suppose you don't have a valid coloring.
Oh, okay, because I need to do it, the verifier needs to be able to do it.
Yeah, the verifier does it. It's kind of operating on the graph.
Sorry. Yeah,
Still, I think it's a useful question.
Yeah.
You're operating on the graph without knowing if it's a good graph or a bad graph. So you still do this transformation, and in the end, you get a new graph. You still don't know if it's a good graph or... So you do this transformation. You don't know if you're in this case or in that case, and you end up here, and you again don't know. Okay. All right. So this side has some questions. You guys... Okay. All right. So what about how do you do this? How do you prove this thing? So the canonical proof uses these low-degree polynomial encodings, these locally testable codes that are similar to what I talked to you about, where you have this polynomial function, it has low degree, and then what the verifier will do is maybe it will look at the line and look if that polynomial is low degree on the line and stuff like that. Okay, and then there is this other proof by gap amplification that somehow builds a PCP iteratively, and it very much resembles the construction of these zigzag expanders. So I want to tell you a little bit about it because it kind of follows in my kind of the flow of my talking about expanders and how how they give from global to global aspects. But I put here item number 3 because I feel like in coding theory we have many different constructions of error correcting codes, and different ones have different features and attributes, and I feel like these gap amplifying encodings, okay, we have these 2 ways of doing them. It's more than 2, like inside one there's many different ways of doing it, but generally there's kind of 2 general ideas, and I feel like there should be more, and to me it seems that this new area of high-dimensional expanders, which I'll touch at the end of the talk, might open the door to more ways of getting this kind of robustness. So I want to just tell you, let's see what we are doing. Okay, I'll tell you a little bit just about how expanders are used in this gap amplification. So we're starting with this problem of three coloring. So we have this graph, and what is three coloring? It's basically telling me, give a color to each vertex so that along every edge, the colors are different. So I can view it as a system of equations. The variables give values from 1 to 3. Each equation is inequality. x1 must be different from x2. Okay. And now I want to construct a graph with a gap, like we discussed. And the idea is to break the graph into small pieces, like we did in all these earlier examples. Break it into small pieces and locally get this gap going, like apply a local PCP on each piece, and then force them to match each other. Like in the expander code where we said, okay, on every vertex I'm going to have a small code word where I know I have distance and everything is fine, and then I'm going to just force them to agree with each other. And I'm going to put this all on an expander. So how do I combine this? Sorry about this. So I think of my graph, my expander graph, and my little pieces are going to be balls around vertices. So every vertex basically looks at a neighborhood around it. Maybe here it's just the immediate neighbors, but you can think of neighbors at some distance. And you basically write down a little PCP proof or a little proof that says everything here, all these colors are proper. There's no problem. And you do it separately for each ball. Then what you want to analyze is, or what you want to require is that different balls kind of say a coherent thing. So if this local view said that these are the three colors here, then this local view should also say the same thing. They should basically agree. And somehow you can prove that using the expansion of the graph, that if there was some mistake somewhere, like the graph is not really three-colorable, so at least one of these balls must lie. It must say something either that disagrees with a neighbor, with another ball, or that is incoherent internally. So none of them will lie internally. It's like in the code. Every vertex will tell you that he has some local code word, but the question is whether he will agree with all of his neighbors. So somehow here, since you're looking at balls some distance away, you're going to force more than just one problem. What you prove is that using the expansion, the problems will propagate. And in one step, they will only propagate a little bit, but if you repeat this again and again, you get this gap amplification. So I imagine this is not very coherent if you haven't seen it before, but basically you do this in iterations, and every time you double the gap. So I don't know if you see this red 2 over here. We started with a gap of 1 minus epsilon. Initially it's like 1 over the number of edges, very, very small, but every time it doubles, and after a logarithmic number of steps, you get a constant. So by the way, kind of interesting, after this proof came out, it was a natural thing to ask, if you continue to amplify, can you amplify the gap to be all the way to almost 1, like between almost 0 and 1? And Andrei Bogdanov showed an example where, no, you must fail at half. So somehow this expander amplification had some limitation, and it remained open if there's some amplification that can work better. We have another kind of way to amplify gaps called parallel repetition. It does achieve a huge gap between 1 and epsilon, but that one doesn't keep the instance kind of linear blow up at every step. It has much more power. And whether or not it can be done with the linear overhead remained an open question, and this was recently resolved in a sequence of works that uses this high-dimensional expansion I don't think I'll talk about it all here. Just to tell you that high-dimensional expanders are these hypergraphs, and there are some spectral properties that define them. And it was initially believed, at least I believed, that this would be strong enough to resolve this question, but it turned out that it's not strong enough, and it depends on also some kind of topological property of these things. They have to do with certain consystolic expansion of these things, which I think Shmuel has been involved in a little bit. So kind of quite, I think to me it's quite surprising that this innocent question coming from PCPs ends up requiring some understanding of certain kind of topological environments, invariants. Yeah. Okay. So last part of the talk, I guess, I didn't ask if I have 15 minutes or an hour.
Well, maybe about 5 more minutes.
5 more minutes, okay.
Irit, so what does 1 versus epsilon mean? Like for, say, 3 coloring, just a random coloring will satisfy, 2/3 of the edges. So
Right,
epsilon means
Means what? Right, so 1 versus epsilon is only meaningful if you think of a larger alphabet. Right? So if you have some kind of million coloring, then a random coloring would only satisfy 1/1,000,000.
I mean, it'll violate one of them.
No, I mean, if you ask if my graph is C colorable or not C colorable, and C, oh, no, that's not a good example. You're right. I need a predicate that like when you do a random assignment, you only satisfy some tiny epsilon, and then you want to prove that maybe some other epsilon is where you're going. So yeah, it may have been confusing when I said 3 coloring. Sorry. I mean, there's a whole, really, like a very large theory understanding different predicates and what exactly is the approximability threshold. And maybe you know, like that for linear equations, modulo P, a random assignment satisfies 1/P, even if it's only 3 variables per equation. And we know that it's NP hard to do anything better than 1/P. So, yeah. Okay. So let me say a few words about locally testable codes. Okay, so maybe I skip all the pictures. So a locally testable code, like we discussed in the beginning, it's an error correcting code that has these PCP properties. What is a PCP property? Even if you satisfy 99% of the constraints, it already means something. It already means that you're close to being in the code. Or contrapositively, if you're far from the code, you must violate a lot of the constraints. So like if your graph was not 3 colorable, no matter what coloring you gave me, there is epsilon fraction of edges that would catch you. So in a locally testable code, the same thing happens. And then it means that if you give me a code word, I can kind of do a property test. I sample a random parity check, and this will give me a good indication of how far you are from the code. And that can be potentially useful for a code. And initially, even the abstract concept of a locally testable code came from looking at the proofs of the PCP theorem and realizing this is the property that these codes have. And this was kind of maybe formally articulated by Goldman and Sudan, but it was present in many of the earlier papers. And all these polynomial codes like Reed-Muller or Hadamard are locally testable codes, but they didn't have a rate that is linear, like good error correcting codes have linear rate. And this was an open question. And in this work with Evra, Livne, Lubotsky, and Moses, we proved that certain kind of high-dimensional expanders give us these codes. I'll just show you one picture. And kind of amazingly, Pantalev and Kalachev, who were working on quantum codes, something completely different, came up with the same construction independently, which is quite amazing. And let me just show you this picture, and I'll end with that. So in these codes, it's like expander codes. Okay, here we are. Where in expander codes, we took a little local code and we kind of stitched it together in many, many pieces along an expander. Here we're taking a little tensor code. I already told you that some of the tensor codes have good local stability, and we stitch them together along a high-dimensional expander. So somehow we make sure that these, like along an edge, like these two labels, they intersect on an entire row. And like along this edge, these two intersect on an entire row. And along an entire square, they intersect on a bit. So you can see like there is a single square in all four of these that intersect together. So really what you have here is some kind of two-dimensional structure where we have these faces and we have these edges and we have these vertices. And we place these tensor codes on this two-dimensional structure. And what this allows you to do is that if you know that some constraint is violated here, it must also be violated here. And I mean, the picture is only partial. So just like before in the case of expander, we said that if you had a single non-zero, then you have more non-zeros and this propagates. You do the same thing about the constraint. You say if you have a single violated constraint, you must have more violated constraints and it will propagate. It's the same kind of using the expansion to propagate some local property of the tensor code globally to the entire thing. And I don't want to keep time, so I think I will just skip this. I wanted to describe how to construct them using two Cayley graphs, one multiplying on the right and one multiplying on the left, and you get these kind of square structure. You put the vertex for every group element and an edge for AG and an edge for GB, and then automatically you will get these squares. And as long as these Cayley graphs are expanding, your entire construction will be expanding. But I think I'll just let go of that. And let's see. Okay, so I think I'll not go into these things. This kind of construction is related to, has many other applications, and it's related to these high-dimensional expanders. But I think enough for today, and
Questions for you?
Okay, so when you defined locally testable codes here, you said like you can property test them by sampling a random parity check. But I mean, is it meaningful to speak of a nonlinear code being linearly testable? I mean, being locally testable? Yeah.
Sure. I think it means you need to devise some kind of distribution over checks. They don't have to be parity checks.
Right.
And as long as you want to have a property that if you're far from the code, a good fraction of the checks will be violated.
Yeah.
And if you're in the code, all the checks will be satisfied.
Okay, so this might be a weird question then, but for a linear code, do those two definitions coincide? Like if I have a linear code and I know that there is some local check, does that somehow imply that the local check must be a parity check?
Oh, are you just asking if yes? The answer is yes. If you have a linear code and you have some checks for it, if you want to have perfect completeness, meaning a code word is always satisfied, check must be linear.
Okay, yeah.
And I think also if you don't want perfect completeness, somehow having nonlinear checks for a linear code doesn't make a lot of sense.
I mean, it sounds weird, right? It doesn't sound right.
Yeah, but I have to say that a lot of codes are not linear. Like you can think of even start with a linear code, but then look at its restriction and require something, and you can stop being linear. So it's not the only class of codes worth using.
Thanks.
Going to the very first part of your talk, somehow, like say tensor codes. I can think of also kind of tensor codes that sits at Spielman. You just have a complete bipartite graph, let's say n by n. And now, yeah, it's sort of my neighborhood is either a row or a column, left on the left.
Right.
Somehow, here you get local testability, but if I sparsify this graph, if I try to use just a kind of bounded degree expander, then I don't.
Right.
But you can rescue this with some kind of maybe a high dimensional expanding object, where you can get local to global for local testability. Is it possible to maybe capture a little more abstractly, like what is this property that allows local to global? I mean, we know examples, but roughly what is the property that kind of allows for this local to global for local testability? Is it the same as high dimensional or some maybe coboundary expansion or something different?
So it's the same as this cosystolic expansion. You can formally define cosystolic expansion where it exactly aligns with this. But when you say capture, I mean, the most extreme would say, if sometime in the future someone proves local testability, they must do it in this way. But cosystolic expansion with the correct coefficients and everything does capture this.
Did the PCP results give you efficient decoding? So in other words, someone gives you a solution that's almost correct to the G prime. Can you efficiently directly get an exact solution to the original one, or do you have to do a self-reduction? Say, okay, now I know the answer is yes, so
I mean, you can. The way you prove the PCP theorem, kind of the proof itself shows you how to reconstruct witness from the kind of noisy, but it's not a local. It's not like. So it means that if you gave me a solution that satisfies 99% of the constraints, there is an underlying algorithm that tells you how to recover. But this algorithm will read the entire thing and will do a lot of things. It will be polynomial time. It won't be like local. Like the ideal thing would be, if I want to now know what this bit here, I just need to read some logarithmically many bits over there. That we don't know.
But you think it should be possible? Or?
Logarithmically many? Yeah, maybe. I think it should be possible to. And locally decodable code means you want to read a constant number. That we know is impossible under certain rate restrictions. Should be possible.
Questions? Thank you again.